In the last video, we analyzed the simple pendulum to find its angular frequency and therefore period. To briefly review, our setup was to first go ahead and find the torque when displaced by an angle theta, then set this equal to I times alpha, which we could rewrite as theta double prime. We then used the small angle approximation to rewrite sine theta as approximately equal to theta, and then we're able to manipulate our equation to look exactly like the spring block system equation, except that this time x has been replaced with theta and k over m has been replaced with g over m. And so via pattern matching, we were able to deduce that omega is equal to square root g over L. Today, we'll pick up from there to start talking about more complicated systems. And to begin with, let's consider a physical pendulum. So instead of having a massless string with a length m attached at the end, let's consider a rod of length L and mass m. And we'll begin by considering the rod pivoted at its edge, and again, we'll displace it by a small angle theta. And our goal is to find the period of this rod. So we'll use the same approach, starting from torque equals I alpha. I'll begin by drawing the forces which act on the system. Obviously, there's some internal forces in the rod, but those are along the axis of the rod. So primarily, we'll focus on mg. And so the torque in this case is going to be negative because it is restorative. Mg is our force. It acts at a distance L over 2 this time. And lastly, we have our sine theta contributors. So that is our torque. We now need to consider the moment of inertia of the rod. And you might recall from earlier videos that the moment of inertia of a rod about its edge is 1/3 ml squared. And again, I'll replace alpha with theta double prime. And so what does this give us? Well, cancel out m, cancel out a factor of L, and let's do some simplification. So we'll have L theta double prime plus 3g over 2 sine theta equals 0. And at this point, I'll divide by L. And lastly, we'll now apply our small angle approximation once again. So we get 3g over 2L, theta equals 0. And at this point, I notice that I can pattern match. We again have theta double prime isolated with some multiple of theta. Therefore, we can say omega equals square root 3g over 2L. So now let's consider the same problem, but what happens if we shift our reference point? So suppose that we're again dealing with a rod of mass m and length L, but this time I'll place the pivot at a distance L over 4 from the edge of the rod. Again, we're going to go ahead and displace this by a small angle theta. And again, I'll draw the force mg, which acts at the center of the rod, uniform density. So in this case, what changes? Well, our torque is now negative mg times L over 4, since we're only a distance L over 4 from the pivot point, sine theta. And we now need to consider what our new moment of inertia is. We can start as our starting point by saying I center of mass is equal to 1/12 ml squared, if you have that memorized. Otherwise, it's a good opportunity to review how to find center of mass via direct integration. But if we happen to remember the moment of inertia of the center of mass, we can use parallel axis theorem to say that I about our current pivot is the I of the center of mass, 1/12 ml squared, plus m times, we now have the distance between the center of mass and our axis of rotation, which is L over 4. So times m L over 4 squared. And sorry for switching between lowercase l and uppercase L there. But this ends up just being 1/12 plus 1/16 times m L squared. So that is our moment of inertia. And at this point, we can put it all together. I'll use my small angle approximation. So we'll have 1/12 plus 1/16 ml squared, theta double prime, plus mg L over 4, theta equals 0. I'm going to quickly multiply the full equation through by 4 so that we have 1/3 plus 1/4. M cancels out. L squared theta double prime plus GL theta equals 0. And so we are just about ready to pattern match. We have theta double prime plus G over L divided by, and let's do some simplification here. So 1/3 plus 1/4 gives us 7/12. And so we divide through by 7/12 to get 12 over 7 theta equals 0. And so now by pattern matching, we can say omega is equal to square root 12g over 7. Now, personally, I find it helpful to always go through this setup when analyzing a physical pendulum. However, often people find it helpful to have a formula to follow, and so let's quickly go through the steps. Suppose I have an object of length L in total, and its center of mass is maybe located right here. So that will be our center of mass. We'll have our pivot point right there. We'll begin by stating that when we compute the moment of inertia about the pivot, it will ultimately look like CML squared, where C is some factor which is dependent on the exact geometry. And we also know that the torque is going to be equal to negative mg times, let's label it x, the distance between the center of mass and the pivot. So it's going to be negative mgx sine theta, such that our general equation looks like negative mgx, I'll go straight to the small m angle approximation and place theta, is equal to CML squared theta double prime. Cancellation in our mass, and we can rewrite this as theta double prime plus gx over CL squared equals theta equals 0. And so our general result is that omega is equal to square root gx over CL squared. So we'll leave it here for our initial analysis of physical pendulums. In the next few videos, we'll look at pendulums which are not as simple as just a rod, as well as ways in which simple harmonic motion can arise in non-pendulum and non-spring block systems.